Well, good morning. And we're going to talk more about TensorFlow. We're going to actually hit some examples. But before we get to some examples, I want to talk a little bit about some of the potential that TensorFlow has, or machine learning in more general sense. TensorFlow is not the only package, but it's the one we're using in this class. Now, as an entire class, there are a number of different major libraries out there that do machine learning and do things in different fashions. And some of them have better performance. I'm not claiming that TensorFlow has the best performance. But as a general approach, TensorFlow has a lot going for it. It's really well integrated with Python. And that's important for us since we're working in Python. There's also a mobile implementation of TensorFlow that allows you to use it on things like iPhones. So there's good integration from that perspective. Google has spent a lot of time developing actual hardware. If you have an application and you want to, train on 5 billion images, that's a literal 5 billion images. Somebody like Tesla Motors, or like their own Waymo self-driving, if you can afford it, these are huge systems specifically designed with hardware for learning in TensorFlow. And these huge systems come in the size of a 40-foot container. So we're not talking a home computer, but if you've got that kind of data and you want to train on it, they are awesome. And also, you have people like Amazon Web Services and Google Compute, where instead of having to buy an entire system like that, they have those systems where you can actually lease a little bit of them and train on them. Now, before we get too far along in this, we're going to talk about what is a tensor and some of the other applications of TensorFlow, because TensorFlow isn't just good for machine learning. TensorFlow is a really good system for a wide variety of scientific computation, because one of the things TensorFlow gives you access to is not just machine learning hardware, but also the graphics processing unit in computers. And it makes it really trivially easy to use the GPU or multiple GPUs in a computer all at the same time and do your computation on those GPUs. And processors have gotten faster and you get more cores in computers, but when you compare, say, a high-end laptop, and mine is pretty high-end that I'm recording this on, it has 12 CPUs. You're not going to find very many laptops that powerful. Compared to right next to it, I have an external GPU. And this laptop actually allows for an external GPU, and it's not a super fast one, but the external GPU has 1024 cores. And 1024 is a little bit bigger than 12, so it gives me access to that with just an additional line of code. And I can do all sorts of computation, matrix algebra, all sorts of things using TensorFlow, besides doing machine learning. So there's some real good reasons why looking at TensorFlow as a general purpose utility makes a lot of sense. But before we get into that, let's talk about why we're interested in Star Wars, of course. Star Wars Legos. Got to have some Star Wars Legos. Why we're interested in things like TensorFlow. Here's an algorithm from a group in MIT that allows them to accurately detect the virus, the pandemic that's going around based on the sound of people's coughs. And it has achieved a 98% success rate, which isn't perfect, as compared to I see in the news that there is a rapid test that actually uses a saliva test. It's not the one we're using here at the University of Wyoming, but there's a rapid test that is supposed to be able to do it in 15 minutes, and it is hitting a 50% accuracy rate, just barely good enough. So something like this that you could just install an application to your phone or onto a phone and have the person just cough at it and it can detect whether or not you have the virus would be a huge thing. Okay? Now, here at the University of Wyoming, they're doing this pool testing. Okay? But, it's not that much fun to go up there and get a COVID test. But here is an example of what they're trying to do and detect it even in people that are asymptomatic. And this is done on top of TensorFlow in Python. So, you look at just a single application like this and you go, wow, this has some utility to it. And when you have something that has utility, what we're going to be building looks an awful lot more like this, okay? Where we're training it to play a game. But training it to play a game doesn't have a lot of difference between that and what you see for training it with a set of data to do something useful. And I know the game training may be, we're going to train it to play this ancient computer game. The reason I picked that computer game, and specifically this kind of a process, is because it gives you good exposure to the technology, not because this is the real utility. The real utility is stuff like this, like testing for things, like automating self-driving cars, for building things that are useful, okay? And the biggest problem with these things that is useful is you have to have a lot of data. The reason we are going to be messing around with using AI and training it for a game is the game can produce the data for us by the system just playing the game over and over and over. Now, what do I mean by a lot of data? I happen to be really interested in bees. I have been collecting data on bees and colony collapse disorder for years. And realistically, I probably have the world's largest high-resolution collection of pictures of bees. I've got a little bit over 180,000 pictures. And I can use some statistical models to show that I don't have nearly enough data to train TensorFlow on the set of bees and actually get the results that I need to get. So there you go. And I've got years involved in this whole process of learning about this problem and trying to approach it and collect data. And I've worked with a whole bunch of different people that have, bee ranchers and then go around and take pictures and stuff like that. It's not nearly enough data. My guess is I probably need somewhere between 300,000 and 5 million images based on the rate of improvement in my models. And collecting the data can be hard. So part of the reason for using a game is that we get the data in a finite time and you can actually let it work and see how it works. Also, when you're talking about this much data, most of you don't have a computer where you can store 5 million images. Certainly not conveniently. And we're going to see that come up in today's demo, is we're going to reduce the size of the images to little tiny ones, but also when you use little tiny images for training, your accuracy is sometimes not that good. So, with all this demand and all this reason, what you would expect to see is that, you want to be a computer science graduate and make some money some years here in the future. They're saying here that the pay range is somewhere in the 135 to 145K per year. That is basically the kind of jobs that you would see on Indeed for somebody that knows machine learning and is basically at the level of a bachelor's student. You've graduated from college, you know some machine learning, and you've gotten a job doing this special stuff. So you probably have a little extra background in statistics, and you've done some projects in machine learning where you can actually apply for a job like this. Now, if, say, you were to go on for something like a master's, okay, or actually publish some papers in machine learning and be a researcher in machine learning, this base salary looks pretty good to me, and this overall median for people that are considered researchers in artificial intelligence, that starts to look like a pretty darn attractive thing. And if you look at this AI pay grades, you'll also see that some people that have done significant research in this are making they're taking home some money doing this. That's because they're solving some big problems in the world, and they've got lots of knowledge about it. Now, this kind of money is going to take more than a bachelor's. It's going to require some effort. But it's nothing that any of you in this class can't do. You can do this if you put your mind to it. You're here at the right time in the right place with a really good AI program here at the University of Wyoming. In one of the podcasts, we're going to talk about what's going on in research here. But you are at the right place in the right kind of circumstances to be able to do this if you commit and you work at it for a while. It's going to take more than a bachelor's, I'll tell you that right now. But it may very well be worth it. When you start seeing numbers like that, you go, I could get into that, you know? Yeah, I could get into that. So here's another article on what it can kind of pay. And they think big bucks is 150,000. I tend to, agree that a software engineer in the Bay Area is making that kind of money. A person in machine learning is making more like 170,000 a year. And the Bay Area may be anywhere in the world these days with remote work. So, this is a pretty good thing, and this is actually coming from a comprehensive IT salary. So this is averages across everybody working in the Bay Area. I wouldn't say everybody, but I think when I looked at the model, they'd gotten something like 60% reporting on tens of thousands of jobs to pull this together. So, this is the kind of stuff that motivates you. Now, we're going to start looking at TensorFlow. I am going to spend some time talking about how you use TensorFlow as other things, but basically I'm going to be working through this set of things from Google on their TensorFlow with examples. I have pulled out, hopefully you have done the homework at this point, where you've at least gotten this piece right here, import TensorFlow, to work. You've gotten it installed, you can actually run something. It doesn't do anything, but you've actually gotten to the point where you've gotten a hello world, you've gotten TensorFlow installed. And from there, we're going to work through this particular example today, which is kind of a simple example. But the first question that comes up with TensorFlow or machine learning is, what is machine learning? And this particular one is a really simple example where we're going to take a data set that just has some numbers, and we're going to learn to curve fit to that data set. It's basically using TensorFlow in its minimal kind of form for machine learning as, does this curve match? And you go, that's all there is to machine learning? Well, in a certain sense, machine learning is anything where you've taken the data and you've extracted some kind of information from it that allows you to perform better in the future. That's what machine learning is. So this one is doing a statistical curve fitting type of model. It's doing it in a series of passes to fit it better to this model. And it has a sense or certain set of things, operations, that it's going to do in order. And those operations are sequential. That's what this thing tells us. And it's going to flatten the input. Okay, and the input is 28 by 28. It's going to have a particular kind of learning model. And it's going to discard some data, and then it's going to learn from that, and that's what these last two do. So these things in combination are going to allow it to match new data to this existing data. And you go, okay, we're matching some data, but that's basically what you do when, you go back and you look at something like this, and you say, what do we have? We've got some sound data. We've got a whole bunch of samples that we've learned from that say, these people out here have the disease, so we've tagged those sound data with, they've got the disease, and these people don't. And we've matched it up with this sound data, so we've got this sound. It goes up and down. It's sound data, okay? I mean, that's all it is. It's some data, and it's classified as in have not. And that's what we're going to do, is a very simple example of have not learning, okay? And we're going to match some things together. Now, by this point in the class, you've probably discovered that, yes, programming can be hard and debugging is difficult. And probably the biggest deal about something like machine learning is we're getting the computer to program itself. This exact same set of code could be used on lots of different data sets to get good results. And as somebody in the machine learning field, what you spend a lot of time working with is, instead of the computer program, you spend a lot of time understanding and working with the data. Okay? This means that the data itself starts to become really important. And the process by which you collect the data and analyze the data and make certain that the data doesn't have internal bias in it, that you've actually worked with the data enough that you understand it, you understand what the computer is getting out of the data and how it does that. And that combination of things is what you're trying to do. Now, in here, we're using a couple different things. There's TensorFlow, and there is this library that runs inside TensorFlow to make it easier to use TensorFlow. I don't know how you pronounce that, but whatever. Keras, something like that. And then we have this other library that we're using for doing some transformations on the data called NumPy. There are a couple different libraries that get used very commonly with data in Python. And one is Pandas and the other is NumPy. And internally, it's using NumPy in here. That's because it has this model and it's going to train, and then it's going to apply this other NumPy function to it to get some predictions. And out of that, we're going to get an array of data. But basically, this entire model is to just specify some things, see it flow through, and see that we get a series of training steps and we get a result that's predictive. So we're going through all these steps. You're more than welcome to come and look at this. We get some output, and finally, at the end of this, okay, we could actually extract the results, but basically we're going to get a prediction of how good this model works. And we're going to mess around with it. So let me actually run the model once. Okay, and I am in Lecture 20 TF homework, because this is where I did the Hello World. But here is the model, and it's 02. It's pretty short. Okay, it's in the lecture notes, but we have import TensorFlow. We have this thing where we're using this MNIST approach, which is a minimizing approach to the differences. We're going to load some data, and it's pulling the data in from the web. So you don't have to worry about downloading it. It just downloads it and then reads it in. So which means you do have to be connected to the internet to run this. Okay. We set up our model as a sequential model. We're going to do this sparse categorical cross-entropy approach. Okay. And we're going to optimize for that. We're going to do some training in 5 epochs. So we're going to do 5 rounds of training, where it's going to train and then correct its errors and train and correct its errors. We're going to go into what that actually does, and then we're going to evaluate the effectiveness of the model. Now, the evaluation of the effectiveness of the model is really saying, okay, I got some data, I trained on the data, but I saved some data back. And this data back, the model has never seen. Now let's see how good the model is with this new set of data and see if it does what it's supposed to do. So say you trained and your effectiveness was 0.25. So it was wrong 75% of the time. You'd go, no, this isn't working for me. Either my data doesn't show what I think it does, or there's something wrong with the data, or... Does that make sense? Now, suppose we run this and we get a high effectiveness, that it finds what it's looking for. Okay? What that means is that if the effectiveness is like 0.95 or 0.98, some number like that, if we get that kind of effectiveness, then we go, yeah, this is good. I had some data, I trained with it, then I used a piece of data I had never seen, and it works on the new data. Now, that doesn't mean it's going to work on any data, but it's indicative of the fact that, yes, now I probably want to do some more testing with some new data sets and evaluate it again and be more careful. But let's run it and see what it does. Okay. Now, keep in mind when you run this, and you probably should, okay, it's probably not going to be this fast for you because I've got extra hardware. But the slowest I've seen is that this takes about 45 seconds to a minute to run this. And you'll notice that in its first training step, there's this loss, and there's an accuracy, and it was 91%, 95, 96, 97, 97. We seem to have kind of petered out of gains in effectiveness, and its total accuracy at the end is this accuracy right here. So we have produced something that when we tested it for its accuracy is 97% accurate. Now, that's not 100%. That means it is going to make mistakes. And we're going to spend some time talking about machine learning and mistakes too, and why machine learning can produce some of the wackiest results you can possibly imagine. Okay, so there are some limits on what it can do. But at least in this case, we got a high 90s kind of result out of it. And it matched some things up. Now, the interesting thing about this is, although, there's some things in here you haven't seen before, basically, you look down this and there's no ifs, there's no branches, there's no loops. It seems like it just listed out a bunch of steps that it was going to do, and then the computer went and did the rest. Which means programming-wise, this is kind of simple. Now, there is this weird from future import up here at the top. And that from future import, okay, allows us to do things in Python on these tensors. Okay. Specifically things like division, and we haven't talked about what a tensor is yet, but it allows us to use division as in this slash right here when we're training, okay? That slash is actually this division package, and it's working on an entire set of data, this X training data. It's dividing it by 255. Now remember I said you want to get your data so it's not weird, okay? This is kind of part of the de-weirding of the data. We read in this data. It's pretty big, but it's not scaled to the correct kind of values. And so we wanted to scale it. So we needed to be able to take this entire whatever a tensor is and divide it by 255. So this isn't like a variable. In fact, this is a matrix of data. And we're going to start seeing in the next example how these matrices of data and what tensors are and how they work together. But this future thing lets us apply standard operations that are pre-built in things like NumPy and apply these operations like division with operators just like it is in a standard, floating point computation where I take a variable and I divide it by a constant. Except here we've applied it, take an entire tensor and divide it by a constant. So when you start seeing things like this and you go, wow, you mean I can do computations on these big things that are tensors, and I can do it just as easily as anything else? That starts to make things like TensorFlow useful in and of themselves. Now, the big power doesn't come in that you can just do that, is that with TensorFlow, it can actually write this program for you and run it on a GPU or set of GPUs in parallel thousands of times faster than you can normally process it. And do that all for you behind the covers without you doing any extra work. Okay, I think I'm going to leave you off at this point with this, and we're going to take a look at the next example and go into a lot more detail.